This is geometry lesson 4.2, reflecting figures. So in 4.1, we just reflected single points. Now we're going to reflect whole figures. So the big idea here says the reflection image of a figure can be found by finding the images of enough points to determine the figure. So what does that mean? So every figure has some points. We would call them the corners or the vertices. And when we reflect them, we're going to focus on those points. We're going to reflect every single vertice of that shape. And that is what would qualify as enough points to determine the figure. We don't have to reflect every single point that's on a line. We can connect one point to create the line. There's an infinite number of points on a line, so it would be impossible to do every single one. But when we reflect a figure, we have to have at least the reflection of each vertex, and then we can connect them to determine the figure. So we are really going to focus a lot in this section on the reflection postulate that states a couple things are true for every single reflection of a figure. All right. So first of all, as we look at this picture, you've got line M, and then you've got two figures if you look closely. This first one, DABC, has been reflected over line M. I know that this is the pre-image, and this is the image because this has the markings. This is the new one. All right, so it's been flipped over. Notice some of the shape was on the left of the line, some of it was on the right. And so C was on the right, it flipped to the left. A, B, and D were on the left, they flipped to the right. If there was a point on that line, it would stay there. That point right there, although it's not named, it stayed there. So if something is on the reflection line, when you reflect it, it just stays on the reflection line. All right, so we're going to look at some properties that stay true under reflections. So first of all, letter A, there is a one-to-one correspondence between points and their images. What does that mean? It means each pre-image has a unique and exactly one image, and each image has a unique pre-image. So that's just putting into words and stating the fact that when I reflect point A, there is only one image of it on the other side. This image of A right here. I can't have multiple A's when I reflect it. Every single point has one corresponding point on the other side. That's A. Letter B. Collinearity is preserved. If 3 points are collinear, then their images are collinear. So basically, the image of a line is another line. So if I was to put another point here, let's call it F. All right, these 3 points right here are collinear when I started, right? They're all on the same line. And when I reflect this figure, the image of F would be here, and the image of D, F, and A now would also be collinear. It doesn't randomly change where now one of them's not on the line. So collinearity is preserved. We're going to be talking about all the things that are preserved here. You have something special, you reflect it, that still remains. It's just on the other side of the reflection line. So what else is preserved? Betweenness is preserved. If B is between A and C, then the image of B is between the images A and C images. The image of a line segment is a line segment. So this is very similar to collinearity. F was between A and D, and when I reflect that line, F, the image of F, is still between A and D. D, this one's important. We kind of already know this. Distance is preserved. Okay, so if we flip something, the image is going to be the same length as the original. So if the image of AB is the image of the original AB, then they're equal to each other. So this distance from A to D, or let's do A to B just to change it up. If that was 10, then I know this is 10. Okay, so distance is preserved. The distance between two pre-image points equals the distance between their image points. We know that. So if you were just given this, you can automatically put it over here. And the other thing that is preserved is angle measure. All right, if you have this angle and it's the image of this angle, then those are equal to each other. So this angle right here, let's say that's 45 degrees. I automatically know that's going to match this one when I reflect it. It's going to maintain angle measure. The measure of a pre-image of an angle is equal to the measure of the image of an angle. So there's 4 main things that are preserved here, and you kind of have to remember them. And so the easy way to remember them We're talking about angles, distance, betweenness, and collinearity. If you look at those first letters, they're not in order here, but we have A, B, C, D. So if you need to remember in reflections, what main things are preserved? It's angles, betweenness, collinearity, and distance. When I reflect across a line, all of those things stay the same. All right, let's go down to example number 1. So we're going to reflect this image, which is the pentagon, 5 sides, 1, 2, 3, 4, 5, over line M. All right, so first of all, point B looks like it's right on line M. So the reflection of it is going to stay right where it's at. So if one of the points is on the reflection line, it stays. So the rest of these points, just like we did in 4.1, you're going to have to go 90 degrees as best you can. If you have a protractor, it helps you be more accurate. 90 degrees to this, and then go the same distance on the other side. So if you need it to be perfect, you would use a protractor and a ruler, and you would measure the angle so that this hits at 90 degrees. And then you would measure this distance and make sure you went the same distance on the other side. So I'm going to put the image of C right here. So A would have to go 90 degrees to the reflection line, and then the same distance as best you can on the other side. And I'm not going to make this perfect right now, but it would be somewhere out here. Same thing with D, straight to that line, same distance on the other side, somewhere out here. F appears to be right on that line, so F is going to stay right on that line. And E, make sure you're not going up, then your shape's going to get distorted. Try and go 90 degrees, form a right angle there, 90 degrees, and then the same distance. It looks to me, E is actually like, if you look at this side, in comparison to how close it is to the line, E looks either the same as D or a little bit farther. So make sure on this side you replicate that. Again, if you wanted to be perfect, you'd have to measure these. All right, and now we're going to connect these. So B connects to A, so the image of B connects to that. Notice A doesn't connect to C, so we want to make sure we don't connect those right there. A then goes through F all the way to E. From there, it goes up to D. D goes to C. C goes to B. Oops, and that line's not perfect. That's okay. All right, and it's not perfect, but that's pretty darn good right there. So we have reflected A, B, C, D, E over line M. So we just go point by point by point, reflect that point, and then go ahead and connect those lines. So again, back to the big idea. The reflection of an image figure can be found by finding the images of enough points to determine the figure. What is enough points? Well, it just depends on the shape. If we're dealing with the pentagon, you need 5 points of reflection to determine the image. Okay, 1, 2, 3, 4, 5. In this case, we had 6 points. But we really don't need F because it's in the middle of a side. So really we needed A, B, C, D, and E. We needed at least 5. 6 is great. It actually made us probably a little more accurate with our reflection. But if I was asking you and you saw the question, how many points are needed to determine the image? You count up the number of vertices and that's how many points you need. If I randomly didn't have the image of D out here, then I couldn't complete this reflection. If I didn't have F, I could still complete this reflection because that's not one of the vertices of this shape. So all of the corners of the shape, depending on what it is, pentagon has 5 vertices along with 5 sides. All right, that's how many points are needed to determine the figure. So we talked about all the things that are preserved through a reflection. Let's talk about some things that are not. So the orientation of a figure is not going to be preserved. So let's read this together. Although reflections preserve angle measure, betweenness, collinearity, and distance, A, B, C, D, they don't preserve everything. The image looks reversed from the pre-image, right? It didn't just come over here somewhere, it's flipped. So when we're talking about orientation, we're talking about the flipping of the shape. So when you think of walking along the sides of a polygon going from vertex to vertex, so here you can see they've created a little image for you of someone walking around it. That's what they're talking about. So as you're naming it and you're going around the outside, either clockwise or counterclockwise, you are assigning an orientation to the polygon. Every polygon has two orientations. The orientation for which the interior is on the right as you walk clockwise. So as you make your way around the outside of this, to the right is the interior. But just think about going around the outside. Think about a clock. We're going clockwise. And if the interior was on the left, or you're going around this direction, then the orientation is counterclockwise. So if the question asks you, what's the orientation of this figure? You're either going to say clockwise or you're going to say counterclockwise. They don't all start clockwise and then go counterclockwise when you find the image after a reflection. This kind of represents a reflection over this line right here, flipped over. Okay, how you determine whether the original or even the image is clockwise or counterclockwise is by looking at the letters. So the name of this one is A, B, C, D, E, and you follow that around. A, B, C, D, E. As that goes around right there, that's clockwise. That's the way a clock goes. This one, as you follow the letters around, A, B, C, D, E, we are going counterclockwise. Now, a couple reminders. When we name these figures, you can, like if you were putting these points on there yourself, you can go either direction to start. So you don't have to go clockwise if the letters weren't already there for you. If you were putting the A, B, C, D yourself, you can put this going counterclockwise. But when you go to name a figure that's already been given to you, the vertices are already named, you do need to follow them alphabetically. Okay, so if this was given to you, you couldn't name this EDCBA and then say, oh, it's going counterclockwise. If these letters were already here, you have to follow them around clockwise, or like it says, you have to walk around the outside following the letters. Now, you don't have to start with A. You don't have to start with the first letter that appears in the alphabet. You could name this starting at C, but if you did, you can't go to B. You still have to follow alphabetically. So you could name this C, D, E, A, B. That's perfectly acceptable. You could start at B and name this B, C, D, E, A. Perfectly fine. But what you can't do is say start at E and then go this way and call it D, C, B, A. That is not allowed. You still have to go alphabetically, but you don't have to start with A or the first letter that comes in the alphabet. You can start with any letter you want, but you still have to follow it around alphabetically. Okay, so over here, if I'm naming this, even though this says flipped and I probably naturally want to go this way around the shape, you have to follow the letters. So the image of A, B, C, D, E, again, you could start with the image of C, but you can't start going this way and go C, B, A. That's not following alphabetically. You would have to go to the image of D, the image of E, the image of A, the image of B, and follow your way around. All right, so notice this is F. This is a continuation of this postulate. Okay, it's got 1, 2, 3, 4, 5, 6 points here, A through F. And so F now deals with orientation. The reason we separated this is because on the front side, it talked about everything that was preserved, and now we're talking about things that are not preserved. When I reflected this over the line, the angles are the same, collinearity is the same, distance is the same, betweenness is the same, but orientation is not. This shape has flipped. It doesn't look the same. Okay, the orientation has changed. So letter F states orientation is reversed under a reflection. A polygon and its image with vertices taken in corresponding order have opposite orientations. So in other words, if a pre-image has a clockwise orientation, when you flip it, its image has counterclockwise orientation, or maybe it started counterclockwise, it will then go to clockwise.